Hello everyone, welcome to this video. In this video we shall see an application of Fourier transform in order to solve the heat equation. The equation with which this Fourier transform started in the very beginning, right? So here the problem is that we are to determine the temperature distribution in a bar. So what we are given? We are given some bar, right, which is given to be very thin. So this thickness is very small. Moreover, it is homogeneous. That means all the properties are same along this length, and moreover this bar is infinite. So that means it is extended to infinity in this direction also and to this direction also. We do not know where it ends, right? So this is given to you, and we are to determine the temperature distribution in this bar, which can be modeled by the initial and boundary value problem. Du by dt is del u by del t is equal to c square del 2u by del t square, where x lies between minus infinity to plus infinity. Why? Because the bar is given to be infinite, and moreover t is greater than 0. T represents time here, so time is greater than 0. So we started from t is equal to 0 and we are marching forward in time. So this is your equation, and in order to solve this equation, what do you require? According to this derivative, you require one initial value in the initial condition here. That means initial condition in time. So accordingly we require the value of u whenever t is 0. So that is given to you in the question here. Whenever t is 0, u, which is your temperature distribution in the bar, so this u is both the function of x represents the spatial direction, so this along this length, and t, which is time. So u is a function of both x and t. So we are to look at the value of u whenever t is 0. So this is given to be f of x in the statement of this question. So this is the initial condition that is provided to us, and moreover because we have second derivative here with respect to x, right? So this is your equation. With respect to x you have second derivative, so that means we require two boundary conditions here in order to solve this equation. So the conditions, they are not given to you explicitly. However, you are given that the value of this temperature is finite whenever we are at the end points, and because this bar is infinite, therefore the end points of this bar would lie at infinity and minus infinity. So we cannot definitely say what are the end points of this particular rod. Okay, so this is the statement. Now what we are going to do using Fourier transform, so we have our equation here in this domain, which is the t domain, right? So or you can call it x domain. We have either the t domain or x domain because u is a function of both x and t. So we are moving on to this frequency domain over here through this Fourier transform. So we'll apply the Fourier transform onto the given heat equation. So we'll be moving in this frequency domain. We'll simplify all the calculations. We'll simplify the problem here, and then we'll move back from this frequency domain to the original domain by applying the inverse Fourier transform to it. So this is the basic structure that we'll be following here. So let us get started with this solution. So for the solution part, we are given first of all, let me write down the equation, the heat equation. So that is given by del u by del t, that is equal to c square del 2u by del x2. So this is our heat equation. Now according to this equation, what we will do, we will apply Fourier transform. We will apply Fourier transform onto this equation. With respect to the variable x, right? So we are not applying it on t, however we are applying it with respect to the variable x, and we are also assuming that the Fourier transform of this function u of u, which is a function of x and t, this is given by capital F of omega t. So that means this variable x has now been converted to this variable omega over here. So this is our assumption. Okay, so that means when you apply Fourier transform on this equation, you obtain the Fourier transform of del u by del t, right? That is equal to the Fourier transform of c square del 2u by del x2. Now you could take out the c square outside because this is a constant quantity, right? Because the material is given to be homogeneous. So this would be del 2u by del x2. And here we have the Fourier transform of del u by del t. Now because we are applying the Fourier transform with respect to the variable x, therefore here the quantity Fourier transform of del u by del t, that would simply become equal to del by del t of the Fourier transform of u, right? And what is this? Fourier transform of u, we have considered this to be the function capital F of omega t. So this is equal to del by del t of capital F of omega t. Now omega is constant, so this derivative could be written as the ordinary derivative only. So we could write this to be d by dt of f of omega t. So this is our left hand side. Now let me call this as equation number 2. Let me call the given equation, the heat equation, as the equation number 1, right? Okay, so now we have the left hand side of equation 2. Now let me write down the right hand side for equation 2. So this is the Fourier transform, c square into the Fourier transform of del 2u by del x2, right? Now you must have studied this formula for double derivative. So if we are to calculate the double derivative of some variable function, so it would be equal to minus iota omega raised to power 2, because here we are having double derivative, into the Fourier transform of this function u, which is capital F of omega t, right? This is how we have defined this quantity. So accordingly, in this case, using this thing here, we will obtain this as c square minus square would become positive, iota square would become negative, so this would be negative c square into omega square into capital F of omega t, right? Using this expression over here. So we have the left hand side as this, the right hand side as this. So we can substitute these. So we can substitute these values in our equation number 2. So therefore, what do you obtain from here? We obtain the first derivative with respect to t of capital F of omega t, right? This is equal to minus c square omega square capital F of omega t. So this is what you got after applying Fourier transform onto the given heat equation. So let me call this as equation number 3. Now we have reached to the stage where we have moved from this x domain to the corresponding omega domain, applying this Fourier transform. So the next step is, so this was our first step, the next step is to simplify the equation here. So here, if you look at this equation 3, this is the first order differential equation where the dependent variable is this capital F of omega t and independent variable is this t, right? So we already know how we can solve first order simplest form of differential equation. This is variables, this could be solved using the variable separable form. right? So using that, I could just separate the variables over here. So this quantity could be written as the derivative of f of omega t, right? And I can shift this to the left hand side so that I would have f of omega t, and I could shift this dt to right hand side, so it would be minus c square omega square dt. And now I am ready to perform this integration. So I have separated the variables. Now we could perform this integration. So integrating both sides, right? So integrating both sides, here you see the derivative of function and the function itself. So it would be log of the function, right? And on the right hand side, we have to perform the derivative, the integration with respect to t. So it would be minus c square omega square t, right? And we have also the constant of integration. So let me call that by log of some quantity k, right? Why log? Because here also we have log. So it is better if you use log, so that you could write this term as log of e to the power minus c square omega square t into k, right? And you have log of f of omega t. Therefore, your f of omega t, this is equal to k into e to the power minus c square omega square t. Now this is the value of the function f of omega t in the omega plane, right? So let me call this as equation 4. So that means we have simplified our expression in terms of f of omega t, which was the Fourier transform of the given function u, right? But however, in the question they are required what is this u. So in order to determine this u from this equation, what we can do, we can apply. So our equation was the Fourier transform of uxt is equal to f of omega t. So we can apply this inverse Fourier transform on both sides, so that it would become Fourier inverse of this function omega t, right? So our third step would be to move from this frequency domain back to our x domain using the inverse Fourier transform. So this is what we will do here. So the next task is, moreover, this thing that is a constant quantity, and we are to calculate what is its value. So in order to calculate this value, what we can do, we can use the given initial condition. So what is the given initial condition? The condition where t is equal to 0. So if you have a look at your statement again, so this is your initial condition. So you are given the value of u calculated at x and t0, that is given to be f of x. So you are given u at x comma 0 is equal to f of x. So what you can do, you can apply the Fourier transform on both sides. So applying this Fourier transform on both sides of this equation, so what do you get? You have the Fourier transform of u of x comma 0 is equal to f of 0, right? It is not f of 0, it is x and t, because we have not yet substituted the value for t here. So we are just applying this Fourier transform. So when you apply this Fourier transform, now you already know the Fourier transform of u, that is capital F of omega t. So this is equal to the Fourier transform of f of x. So I can also define this quantity as g of omega, say, because, so if I write here, we can assume the Fourier transform of f of x, which is according to definition integration from minus infinity to infinity f of x e to the power minus iota omega x dx. So I'm calling this as g of omega, right? So I'm using this g of omega here. So that means you have f of omega t is equal to g of omega. So now if you substitute t is equal to 0 here, so you have f of omega 0 is equal to g of omega. And so this is one value, and you can also use your solution. You have f of omega t, this is equal to k e to the power minus c square omega square t, right? So substituting t is equal to 0 in the equation number 4, so we will have f of omega 0 that is equal to k would be as such, and in place of t we will write 0 here. So it would be k e to the power minus c square omega square into 0. So it would simply be equal to k. So therefore we obtain f of omega is equal to k and f of omega is equal to g omega. So therefore this implies k is equal to g of omega. So we obtained the value of k from here, and you already know what is g omega. That is the Fourier transform of the function f of x. Now this function is given to you in the statement of the problem, so therefore this is also known quantity. So we do not have to worry about this. So this k also becomes known now. Earlier it was unknown quantity. So once you have this, so you could substitute it back into your equation f of omega. So therefore your f of omega t, that becomes, it was k into e to the power minus c square omega square t. So it now becomes g of omega e to the power minus c square omega square t. So this is the simplified version of your heat equation in the Fourier domain, in the frequency domain. So the next third step is to apply inverse Fourier transform on both sides. Because at the end what we are required the value of u of x of t, which represents temperature. So this is the inverse Fourier transform of capital F of omega t. And what is this? Capital F of omega t is equal to g of omega e to the power minus c square omega square t. Now what is the definition for this inverse function? So according to this definition, we have 1 by 2 pi as such integration from minus infinity to infinity, whatever is the function that is given to you, e to the power iota omega x dx. This is not dx, this is d omega. Why? Because we are now shifting from omega domain to the x domain. So we have a positive sign here, and the function that is given to you is this one. So you will write g of omega here, e to the power minus c square omega square t here, right? So this is what you have. Now you can also substitute the value of g of omega. So when you substitute the value of g of omega, so what was that? G of omega was your Fourier transform of f of x. So we could substitute this value here in place of g of omega. So therefore we have 1 by 2 pi integration minus infinity to infinity. In place of g omega, I can write minus infinity to infinity f of the function x e to the power minus iota omega x dx. And in order to differentiate it from this integral, so I could change this variable. So because this is the dummy variable for used for integration, I could use it some other variable also. So this thing becomes equal to f of zeta e to the power minus iota zeta d of zeta, right? And we have the other term as e to the power iota omega x d omega, right? So now I could club these values together. So it would be 1 by 2 pi integration minus infinity to infinity integration minus infinity to infinity f of zeta e to the power minus iota omega. So clubbing these two terms, I have zeta minus x into e to the power. Also we had this term, right? I skipped that here. So it would be e to the power minus c square omega square t. So it would be e to the power minus c square omega square t d omega d zeta d omega, right? So now we can substitute in place of this. So you know already e to the power iota theta, that is equal to cos theta plus iota sin theta. So utilizing this expression over here, so we can split this into two terms. So one is including cos theta, so it would be cos of theta. Theta is this whole thing with a negative sign. So we would have and cos of minus theta is cos theta, right? So we could use this term so that we would have omega zeta minus x and all these terms as such. So this is our first term, and then we have minus iota. Why minus? Because in the angle we are having minus. So minus iota integration minus infinity to infinity integration from minus infinity to infinity, all these terms as such. However, in place of cos now we will be having sine, right? So it would be sine of omega zeta minus x, yes, zeta minus x e to the power minus c square omega square t d zeta d omega. Now all of you know that this sine, that is an odd function. So accordingly this integral over here becomes equal to 0. So whole of this integral becomes 0. So we are left with this first integral only. So that is equal to 1 by 2 pi integration minus infinity to infinity integration minus infinity to infinity f of zeta cos of omega zeta minus x e to the power minus c square omega square t d zeta d omega. So this is what? This is the temperature profile that we were looking for from the very beginning. So this is nothing but, this is the solution of the given heat equation. So according to this solution, we obtained this Fourier transform that you already know. So you could very easily use this Fourier transform in order to solve the given heat equation. So I hope you understood this problem well. Well, that is it for this video. Thank you for watching.